Hi everyone, I'm Luka. I'm principal engineer at Reversing Labs, where I'm running the team that's responsible for downloading the internet. So we try to gather as many files as we can, and that's a large amount of files from all corners of the internet. And you might wonder why we would want to do that. So we, as a company, have one of our goals is that we want to be able to give you all the information possible about any file you can ask us. So no matter what file you have, we'll tell you what the file is, what it does, etc., etc., etc. To do so, we run around the internet, collect everything, scan it, etc., etc., etc. Our main objective is to find files we need to, they're interesting to us, and run them through 40 AV scanners, through our in-house solutions, etc., so that we can reverse engineer them back to their functions, basic functions, and tell you information about that file on the level what API calls it's doing, what network calls it's making, and I know what IO operations it's doing, and so, stuff like that. Now this goes beyond the simple, is this file a bad file or is it a good file? So we are even able to tell, in certain cases, if the executable was written by the same person or the same group. This is all done in pretty much millisecond time for each executable file. Overall, our process is quite simple. So we have to first find all the possibilities on the internet that we can download. We filter out those possibilities to those that are interesting to us. We download them and we store them for processing. Then, during the processing part, we extract all archives and unpack all interesting samples. Unpacking means that we extract files embedded within files. So if you have installation files, or you have resource files, or DLLs embedded in your stuff, we can unpack it and extract everything from the inside. We push that through our system for scanning. So 40 AV scanners, static analysis by Tycore, dynamic analysis, and we gather all of those reports, store them in the database for serving to our customers. And finally, we have a system that provides search and querying and pushing of all of that results to our appliances, to clients, to customers. So what we're basically doing is Pokemon hunting. So we got to catch them all. And we got to catch them all as soon as they pop up. And to do so, we need to cast our fishing nets as wide as possible, so we can get the files as soon as they appear. So broadly speaking, we can split our sources of files in 3 groups. So we have verified sources of goodware files. Those mostly come from large software vendors. Some of them share their software openly with us. Some of them even scan their software with our solutions and share the results for us. And some don't, so we just scrape their websites and just take everything they have. Next up, we have the grayware content. And this is the content on the web that we don't know what it actually is. So this is mostly the stuff that's been left open on the internet without authentication that we can grab. Be it open FTP servers, S3 buckets, blob storages, directory listings, whatever. So these are pretty much low reputation sites, which don't have a lot of content, but of that content they have, some content is good, some content is bad. So we just grab everything and push it through the system. In addition to that, we also have software aggregator sites like Download.com, Softpedia.com, etc. We just take everything from them too. The third group is the bad guys. So we have in the wild malware hunting. This is mostly exchange with security companies, partners, government organizations, private groups, etc., with which we exchange malicious samples between us. We also do our own malware hunting. So we build honeypots and we collect NNTP servers and torrents, etc. To get as much as malicious content as we can. So it pretty much all seems very straightforward and simple, and until we get to the scale at which we are trying to run this. So Each and every file that is determined to be interesting to us is run through, like I said, 4 scanners and tie-scale and dynamic analysis, etc. And not only that, we also rescan all of the files we have, not all of them, but again, the select few that we have on some period. So after 2 weeks or 6 months, we rescan it. So if anything changed, the detections changed, or antivirus companies detected new viruses, etc., we rescan it so we can get new detections. Now, like I said before, so if you can see here, I say 3 million harvested, 6 million analyzed. So the difference between those two numbers is the fact that we extract files from video files. So we harvest 3 million a day, we analyze 6 million files a day. All of that pretty much generates 800 million events a day. Those are events we store for 30 days in short-term monitoring storage. That's 30 billion events that we have in short-term storage. In total, in long-term storage for this year, only up to now, we have 280 billion events. That's individual records that we can query online and search online. All of that gives us some 5 billion analyzed files. So our database is 5 billion files. So for 5 billion files, we can tell you what those files are and what they're doing. Not only that, we can tell you which files are similar, which files are not similar, etc., etc. Pretty much that consumes 4 terabytes of storage per day. We're at 4 petabytes of storage right now, where we think by like March next year, we'll be at 4.5, maybe 5 petabytes of storage that we're consuming. We serve that to our customers through our APIs at a rate of 3.5 terabytes per day. That's excluding our appliances that sit in-house with our customers. So this is the scale we're trying to run things. And this 3 million that we harvest, like we'll see, we would like that to be much larger. So before we start designing and building our system, etc., we have to paint a tiger, so to speak, so that we are all aware what we're designing and why we're designing it. So to start off, we have our objective for our system. That's the harvesting part of this entire system. So we want our system to be a self-balancing, sustainable system that will meet the demands of sample harvesting in the period of 3 years. So this is a general vague sentence, means pretty much nothing, etc., etc. But we have 3 keywords here. So self-balancing, sustainable in 3 years. We want our system to be self-balancing. That is vague on purpose because at this point, when we started, we didn't know what self-balancing is. We didn't know what kind of complexity we can achieve. We didn't know anything about it. But we knew that at the scale we were running something, it needed to be some sort of self-balancing so that we can manage it. Sustainable, again, is pretty vague and in general. Our system needs to be sustainable at any scale we're running. So I'm going to show you the numbers we're increasing load, but we need a system that we can, as everybody, that we can easily manage, evolve, and upgrade as the need arises. And the period of 3 years was selected because pretty much in 3 years, the whole IT industry could change, and there's no point of thinking about in a period of longer than 3 years. So to clarify our objective, we defined some key results that we can actually measure something against, that we are doing something concrete. So we want the red numbers are the actual current state, and the green numbers are the future state that we want. So we want to increase our number of sources 15-fold, 15,000. That means 15,000, that's not domains, that's 15,000 sources. Behind those 15,000 sources, there could be 100,000 domains, doesn't matter. We want to increase 5-fold the number of samples to 10 million a day, and the size of samples we are ingesting a day, we want to increase it to 15 terabytes a day. So this is something that we can measure ourselves against. When we build our system, this is some, let's say, performance indicators or something like that. Rocco has a talk on OKRs at 3 and track 3. You might want to check it out. So this is our target. This is what we're going for. Okay, so we got our target. Now we have our existing system. So before we get into coding and stuff, it's really important so that we surface the specifics of the system. Now, if we just jump into coding straight away, there's really a lot of stuff that we are not aware of because stuff works as is and you're not aware of it. So it's really important for us to bring that up to the surface just to prevent us from hitting rock bottom way too fast. So at this point, when we started this, we didn't even know if we want to just upgrade our existing code base through some extensive refactoring, or we should just go and start to write everything from scratch. So what we did 3-4 day, something like that, retrospective of our current system, and simply wrote everything down in a good and a bad category. No fussing about, just good and bad. So some stuff ended up in good and bad. Interestingly enough, stuff ended up on both sides of the fences. The same stuff ended up on both sides of the fence. So we wrote everything down. It was obvious that when we wrote everything down, it was obvious that our decision to do the respective and try to surface the specifics was, well, needed because the bad outnumbered the good 4-1. And most of the good wasn't even tied to our code base. It was tied to other systems and support and stuff like that. So starting anew also meant, when we saw this, starting anew also meant then that we could think about our system in a different way, in a new way. So clustering. So we grouped up all of the similars because all of the stuff was repeating itself and stuff like that. We grouped up all of the similars, and then we further grouped them into themes so we can easily more easily manage them. And this process also yielded a lot of open issues that we need to resolve regarding our existing system and regarding tying us into the existing system. And then we wrote out our dependencies just to round up the entire picture of what the system is. As you can notice, probably, most of our requirements here, if we can call them that, are like just a couple of words. So at this important time, didn't have any sense to waste more time and energy to further define the requirements into details, as we didn't even know what we were going to do in the system. So next up, when we got our targets and the specifics and stuff like that, we took an architectural look of the system and what the system is currently doing. So the existing system was built over the years by various people, piece by piece, as something was needed. And it became quite fractured between different environments, platforms, programming languages, and people maintaining it. So the biggest problem was that the system has different implementations, processes, names for the same thing in different parts of the system. So we do the same thing 5 times over differently in different parts of the system. What we did, we broke everything down to its basics and standardized it so that we boiled down some 40 services to just a couple of stuff that we have here. Okay, so time to make some decisions. We have requirements, basic design. We have the specifics, etc., etc. And now we have to make some decisions about how we're going to build our system. This is, this year's ChangeCon says be a hero. I say don't be a hero. Well, when you do something like this, you really need to be sensible about what is critical that you do yourself and what is just good enough. So you have to accept the good enoughs. One of the post-its on our respective had just one word on it. It was Mile. And Mile is an actual person, and he's the personification of services provided to us by our backend team. And one other post-it had 3 weekends on it. And Mile and 3 weekends have a lot to do. Our backend team monitors a lot of our systems, and they pretty much provide 24/7 monitoring of the entire system. And when something misbehaves, they squash it to restore the system back to its normal state, and everybody's happy. And to do so, they require us to use a certain set of tools that they use so they can do their job. So for us, that was the price of having 3 weekends. if we want to have free weekends that we don't have to monitor everything ourselves, etc., we have to use their tooling. And that's the price we accepted, gladly paid, so that they can do the weekends and we can just go home. Next, we had to select which Python versions we would use. So my colleagues were very skeptical. We were using Python 2 up to this point, and we were talking about moving to Python 3. And they're very skeptical about leaving back the libraries that were in place and were working on for years and writing them from scratch. So it was a dilemma between, are we going to use the code we know that works, or are we going to write the new code and use the new version of Python? Because it doesn't make sense that you will write a new system on an outdated version of software which has bugs that pain you. So we did some trial runs, and we proved ourselves that we can do it, so Python 3 was the way to go. The point of all this is to be careful to pick your way, because you might get hurt. So you come to a conference like this, and everybody talks about new stuff, Apache Storm, Kafka, yada, yada, yada. And you come back, and then everybody wants to do the cool new stuff. But all of the cool new stuff has a price attached to it. Be it that you need to learn something new, be it that it's not properly tested, being that it's not in mainstream development, etc. So you really need to understand what problem that piece of software solves, and are you willing to pay the price to use it? So let's get back to the specific problems we face. When we talk about what we're trying to do, there are 3 specific problems we need to take care of. First of all, which is tracking files across all of our sources. We want to track all of our sources for changes in their content. We want to detect those changes and queue them up for processing. Now, we said that our target is 10 million samples per day. We estimate that we will need to discover 20 million URIs per day to achieve those 10 million. Now, when we discover 20 million URIs per day, we don't want to download all of them because, well, we don't want to waste our bandwidth. So we have to run it through the duplication. The duplication is a specific problem here, is URIs don't uniquely describe a file, etc. But more the problem is the scale. So if we run 20 million URLs through the duplication a day, that means that we will have a database of 500 to 700 million URIs at the end of the year. And we need to run it at the rate of 300 per second at minimum. So we need to have a system that can, with 700 million records in a database, can run 300 queries a second. So that's the specific problem here. Right now, we just went for the basic stuff. We put Postgre in there, and that's going to be a mess in a month or 2, whatever. But we'll have to revisit that in some future time. So when we get our 10 million samples, we just queue them up and wait for downloads to finish. Now, our industry is a very time-sensitive one. And the rule of is who has the sample first is the king. That means that we need to get our samples in as near real time as possible. To get the files as soon as possible, we need to check our sources very often. Now, when we check our stuff, we need to match our checking interval with their update interval, so we don't, kill them. Because if we check it too often, they're gonna freak out. So we need to try to figure out how often they put up new content, so we can get it as soon as possible. The second problem here is downloading. When we get to downloading, we could surely deploy 1,000, 2,000, 5,000, whatever, 1,000 services for downloading, and try to process as many users as possible. But the problem is that really doesn't work. So the way we discover URIs pretty much guarantees that they will be queued up in order by source. That means that when we start 1,000 downloads at the same time, all those 1,000 downloads are going to hit the same server. And that means that we are going to max out their upload speed before we max out our download speed, bandwidth. So that's no good. What we want to do, we want to parallelize downloads in a way that we max out our download bandwidth before we max out our target's upload bandwidth. So we try to achieve this by, it's simple. You just limit the number of workers per domain, and that limits the download speed. But to solve all these problems at a scale we're trying to run and everything, we need to be a little bit more clear than that. So right now we're just doing that manually, limiting and everything manually. But as we go on and manage more sources, we can't do that manually. So that's the part where we want to introduce that self-balancing part of the system. So we want the system to be able to detect itself the download speeds and adjust the number of workers based off those download speeds. The same way goes with the detecting changes. So we want the system to be able to detect what the period is and adjust the check intervals to the period of their updates itself. So we're working on that right now, and it's not that difficult of a problem, but it takes time to work it out. The third problem is, don't get caught. So we harvest files from various actors that are good guys and bad guys and stuff like that. Either way, you don't want them to know what you're doing. So the good guys really don't like when you're hammering their servers, disrupting their services, etc. So they will ban you, of course. And the bad guys, well, they don't want security companies to know what they're doing. So we need to hide what we're doing. So with the bad guys, it's a bit more dangerous because the bad guys can launch DDoS attacks, hackings, and other attacks on your infrastructure, so we need to be more careful with them. To fight that, so for the good guys, we just use rotation of 127 IP addresses across the board to rotate the behavior, rotate their requests, and we introduce various cooldowns between requests so that we simulate human behavior, let's say. For the bad guys, we use VPNs, Tor networks to proxy our requests to cover us, so that it doesn't seem that it's us. We can't really use any cloud solutions here, because cloud providers will detect malicious content and will kill you off, and that's not what you want to do. So before we start coding, we need to break down our work so we can track it. So we're working on a system that, let's say, we know every feature it will have, so it's perfectly okay to say, let's each take one service and let's write it out, and we will be done really fast. We're also building microservices, so it's kind of natural, just let's go build service by service and we'll be done. So that has a couple of problems with it. When you do stuff like that, building service by service, developers get boxed into thinking about their individual service they're writing, and nobody pays attention to the whole system. Then you have problems that spin off of that. So you have problems like my service works fine, and then finger pointing and blame games. You have problems like I don't want to implement this in my service, he should implement it in his service, and all that, children like squabbling, etc. But the main point is that you break up your team into little small groups of people, each fighting for their own service, and nobody pays attention to the whole product. So after we do all the coding, we try to run everything, so then that's the time when usually when we do stuff like this, we figure out that the stuff doesn't work. So that's the time when you figure out, oh, we put months of work into this, and then we have new months of work ahead of us just to get it up and running. Not to mention that trying to explain what you're doing to anyone, even to yourself, and what you have achieved so far is really difficult. So what did you do? You just put some methods into some services, and that's it. Nobody saw it running in production, nothing. So the team has no sense of achievement. It just sees work, and more work, and that's pretty bad. So we decided to break our work not by services, but by sources. We would develop features and services, etc., when the need arises for each source. So we build our system of sources and not of services. Our sources are a business value deliverable that everybody in our company understands what is, from the developers to management to whatever. So we all understand what you're talking about when we say source one. This approach turns the drawbacks from the previous approach to its strengths. So now as we build sources one by one, the developer that's building sources, the developer that's building a source has to think about the entire system all the time. So he can't just do some feature in service N and that's it, I'm done. No, when you are done with source one, you're done with source one, and that source one works and can be pushed to production. This is simple, measurable, reportable. You can see impacts very fast. So depending on source, it takes us a week or 1 day or something like that, but you can see results real fast. This approach forces people to collaborate, to share coding standards, and generally forces collective code ownership because everybody's touching everybody's service. So there's nobody who has ownership of a certain piece of software. But not everything is so great. So when you do stuff like this tends to introduce suboptimal code into services, duplications, etc., etc., etc. So that we try to combat with code reviews, performance tests, and stuff like that. What's even worse with this is that it introduces a lot of churn into your development effort. So, but also as you can see, as we progress with adding more sources, churn will drop really fast, and it drops really fast because the internet operates on a fixed set of protocols. There are not an infinite number of protocols that the internet operates. So as we add more stuff into the system, we get more stuff to reuse, and and at one point we'll just be adding new definitions into configuration, and everything will be running as is. After all that, doing our basic design and trade-offs and whatever, it's time to do it so that we do some finally do some coding. And we're done. So coding is fast. You know, developers kind of tend to know how to code. Coding is never the problem. If you break down the work properly, coders will code it and it's done. After all of that, when we put everything back together, this is what we ended up with. We ended up with some 12 services running in 500 instances. And of course, as we migrate more functionality of the existing code base, the number of services will grow, the number of instances will grow. But still, this is a fraction of a code from the existing system. So the foundation, so we can split our services in 3 groups. We have foundation. This is just the supporting cross-cutting stuff that other services rely on, notification config, adapters to existing systems, libraries, etc. Then we have the brawn. So that's our muscle that does the work. They do the actual work. They're very simple services, stateless, scalable to infinity. They usually have the same pattern, like 3 queues, just take a message and push it out to the output queue and be done. And then we have the brain. The brains are heavy logical code. They have state, multiple input-output queues, and etc. And they manage the work the brawn does. So they don't have to be as scalable, but they contain all of the smart bits and pieces. Next up, this is our operations perspective. Now, our operations perspective is the management of 15,000 sources at that scale. So we need to have it sustainable. It's not sustainable that if we manage 15,000 sources, by the way, there's 5 of us in the team. So if we manage 15,000 sources to 5 of us, that's 3,000 sources per person. We can't do that manually, no way. So sustainable operations is extremely important for us. First off, we have procedures. Now, everybody frowns on procedures, whatever, but we don't follow them blindly. We don't follow procedures blindly. We just use procedures to double check everything you do. Procedures with vision tests also give us the second, another thing. They give us the specification of our system. So we don't have a specification of anything we're doing. Procedures plus written tests, unit tests, whatever, integration tests, whatever. They give us everything we need to know about how our system should behave. Next up, we have metrics. So to manage everything about these sources, we have to have metrics that we can track. These are all metrics set up at a global level. So we don't track every message service or something individual. We just have global levels with metrics and some upper and lower bounds of normal operations. So when something happens, steps out of normal, then we just go dig a little deeper until we get to the root cause. And finally, automation. Automation enables us two key things: repeatability and elimination of humans. Humans are the worst. So when you eliminate humans, that results in lower workload, less frustrations, less errors, and everything. So eliminating humans from every possible thing you're doing is great. So what did we learn? So first thing we learned, plans are expendable. Our first plan was like a month long. We invalidated it within 3 days. So after 3 days, that plan was out the window. So from then on, we used mostly PDCA. We would plan at the start of the week, set up some assumptions, work off those assumptions, get some results, and if those results were satisfactory, we would put that into our product, into our process. What this allows us is to evolve really fast. We don't pretend we're perfect, but we make failing really cheap. So on a weekly basis, we do a lot of assumptions, we do a lot of tests, and then we drop everything that can go in the system and can't go in the system. So where are we now? We have done some theoretical testing of our system, and we figured out that we can push some 8 million files per day through our system. And it's a bit short of the original target, but it's still some 3 times over the existing system. And I'm done.
You're done, exactly.
Thank you.